Hello and welcome to this lecture, which I'm going to talk about how to use Gauss's and Ampere's theorem to calculate or determine magnetic and electric fields. For example, the field of a point charge, of a charged wire, or of a solenoid, or of a current-carrying wire. So let's maybe start with discussing how the laws actually look, and then explain them by a few examples. The first law is Gauss's flux theorem, which looks as follows. So integral over e dA equals q divided by epsilon 0. Okay, what does that mean? That means basically if you have a closed area, which is symbolized by this A and by this loop, so we have a closed area which encloses some kind of volume, then we're basically counting how many electric field lines are penetrating the area which encloses the volume. So that's basically what this integral is saying. It's saying, okay, multiply the electric field with the area, which gives you somehow a number which represents the amount of field lines, and that one is proportional to the amount of charge in the volume, which is Q. So that Q here stands for the charge which is in the volume, which is enclosed by the area AA. So that's basically what Gauss is telling us. The more charge there is in the volume, the more field lines there are which penetrate the enclosing area. Okay, and then there's Ampere's circuital law, which states something quite similar. So we have again an integral, which is of a closed curve this time. Let's maybe call the curve, I don't know, C. And then it's B times ds equals u0 times I, which is again quite similar to Gauss's theorem. Basically, we now have a curve, a closed loop, for example, like that, and that one encloses an area now. And the question is, how many magnetic field lines are lying on this curve? So, for example, if we have a magnetic field which looks like that, so there's a current-carrying wire looked from above, and the field lines are going round it. Then we can talk about, for example, a way C, a closed loop C, which goes like that. And then we're trying to multiply the magnetic field vectors with this way. So the field vectors are pointing that way, and the closed loop vectors are also pointing that way. So that's going to give us a positive value for the integral, and that one is proportional to the amount of current which is passing through the area which is enclosed by the line. So in that case, we have a wire, that one, in the middle of the area, which penetrates the area. So there's an intensity, a current flow going through the area, which means that there must be some magnetic field lines along way that closed loop. So basically what Gauss's law is telling us, that the amount of electrical field lines going through an area which encloses the volume is proportional to the amount of charge in the volume, and Ampere's law is almost the same, only for closed loops which enclose an area, and it counts the amount of intensity or the amount of current flowing through the area proportional to the amount of field lines going along the closed loop. So let's maybe try and use Gauss's theorem to calculate, first of all, a very easy thing, namely the electrical field of a point charge. So example A for Gauss's theorem is a point charge. Okay, so let's imagine we have some kind of point charge in the middle, like Q. And now our goal is to evaluate the electrical field around the point charge. So let's just define a closed area around the charge, because the point is, no matter which area you choose, the integral will always be the same value. That's the point of Gauss's theorem. So I can choose my area like quite wobbly around Q, doesn't matter. I could also choose it quite symmetrically, which is my goal. So I should always try to use the symmetries we have in this problem. So the symmetry would be a radial symmetry, which means I would choose a sphere as an area. That should be a sphere of radius r. So we can calculate the electrical field at the radius r, or at the distance r from the charge, because it's symmetrical. So the electrical field over here should be the same as over there, because it's symmetrical. So there's no reason why it should be different here from here, because space is symmetric. Space is isotropic, which means there's no preferred direction in space. So we can use that one in order to use Gauss's theorem. So let's just write it down again. So it's the integral closed area, EDA equals Q divided by epsilon 0. Okay, so the closed area is given by that one, so you can imagine it like three-dimensional. So there's this Q in the middle, and then we have a surface area, a sphere area around the charge. Okay, so let's just think about what happens here. The nice thing is, because this electrical field is symmetrical, it goes radially outwards. So it looks like that. So electric field is like that. Oh, goes from there, and so on. And the nice thing now is that the area vectors are always standing orthogonal to the area, which means the area vectors look somehow like that. Orthogonal on the area. That's not quite orthogonal. There we go. So that might be a dA vector, or that might be a dA vector. So the nice thing here is that these area vectors are always parallel to the field vectors, which means we can ignore the vector characteristics of these two numbers, which means in that case, because E and dA are parallel, we can say that this is equal to E times dA without the vectors, because if two vectors are parallel, we can multiply them by just multiplying their absolute value, or their length, basically. So that's due to a law which is called A vector times B vector equals A times B times cosine of alpha, where alpha is the amount of degrees, the angle enclosed by these two vectors. So in that case, that would be 0 degrees, obviously, so the cosine is 1, so we can just use A vector times B vector is equal to A times B, which is quite nice for our integral, because in the end, that's going to make the whole story quite easy. Equals Q divided by epsilon 0. Okay, so we're just adding up all the dAs, because we can, like, E is a constant, because E is symmetrical, so all over the surface E is constant, so we can, like, pull E out. So we have E times integral dA equals Q divided by epsilon 0. And now we have to ask ourselves, what is that part? Well, that part just sums up all the dAs. So the idea of an integral is that you have infinitely many infinitely small parts, and you sum them all up. And what do you get when you sum up all the little area parts from a sphere? Well, you get the whole sphere. So this integral is just the surface area of a sphere, which amounts to 4 pi r squared. That's just a formula you can know from your formula books. And there's E, and that gives us Q divided by epsilon 0. So we can pull that one on the other side, which gives us E equals 1 over 4 pi epsilon 0 times Q divided by r squared, which is the known Coulomb's force, or Coulomb's law, for the electric field, derived from Gauss's flux theorem. That's example 1. Just always try to identify some kind of symmetry, then put some area around the charge which is closest to the charge, and think about maybe whether the field vectors are parallel to the area vectors, and then you can go on calculating the electric field quite easily. Okay, next example I've thought of is a charged wire. And again, same problem here. So we can imagine maybe a wire which is going like that. And that wire has some kind of length charge density, gamma, which means I can write that down. So that's gamma. So length charge density, gamma, which is, well, lambda, I meant to say. Lambda, which is measured in charge per unit length, because this wire can be indefinitely long, so we can't really define the amount of charge on the wire, but rather the amount of charge per unit length on the wire. So we have a charge density of lambda, and then the question is, how strong is the electric field and distance r from the wire? So we can again try to put something around the wire which is symmetrical, and a sphere is not the fitting form this time, but rather I use a cylinder, because that one is has like some kind of translation symmetry. So we can use a cylinder and put it around the wire like that, and then we can use the cylinder in order to calculate the field again. So again, the field looks like this, so it should go radially outwards. So again, we can see that these field vectors are parallel to the area vectors, to the normal vectors of the area. So we can again use that E times dA vectors is always equal to E times dA without the vector arrow on top, which means we can again write down Gauss's law. So integral A E dA equals Q divided by epsilon 0. So we know that one is equal to, again, E times integral dA without the vectors equals, so what is Q? Well, the amount of Q which is enclosed by the cylinder depends strongly on the height of the cylinder. So let's maybe say the cylinder is, or has a height of h. So if there's lambda charge per unit length, then our charge in the cylinder is obviously height times lambda divided by epsilon 0. Now we can think about what the area is, which is penetrated by the electrical field. But it's just this area over here. So that one. So top and bottom are not penetrated because the electrical field is parallel to top and bottom, so they're not penetrated by electrical field lines, only this part of the cylinder, which means we have to calculate this area, which can be looked up in some formula corrections again, which will be 2 pi r times the height. And then we can pull this stuff over here again. This h cancels out, and we're left with E equals 1 over 2 pi epsilon 0 times lambda divided by r, which is the electrical field in a distance of r meters of a charged wire. Okay, let's maybe do one last example, namely a plate capacitor, which is also quite famous for its many applications in physics. So a plate capacitor. Maybe try for yourselves first, and then you can look or watch my solution. So there's one plate, and at the bottom there's another plate. Maybe let's just focus on one plate because that's far more easy. So one plate, and then the field of a capacitor with 2 plates would be double the force or double the field, obviously. So let's just look at one plate with a charge density of sigma. So again, sigma is a charge density per area this time, so charge per area. And let's again make our area a cylinder like that. And again, our electrical field will be symmetrical in both directions, and our normal vectors of the area will be like that. So dA and dA and the field are parallel again, which means I can write down my Gauss law, so EdA equals Q divided by epsilon 0. And again, I can pull this E out without the vector times integral dA equals, well, what is Q? Q is the amount of charge which is in the cylinder. Well, the cylinder has a circular cross-section with the plate. So it's like the cylinder is like that. So the question is, how much charge is on this circle? Well, we know the charge density, so we just have to multiply the charge density sigma with the area of the circle, which is, let's just call the radius r. So the radius of the cylinder should be r. So the area of the circle is pi r squared divided by epsilon 0. And then the amount of area which is penetrated by the electrical field is obviously the top one and the bottom one, because these two are penetrated, which means we have E times 2 pi r squared, which is 2 times pi r squared, so 2 times top, bottom and top, which gives us sigma pi r squared divided by epsilon 0. That one cancels out with that one, and we're left with electrical field is sigma divided by 2 epsilon 0 for a single plate. So that means a 2-plate capacitor will have an electric field of sigma divided by epsilon 0. So double that one. times 2. Okay, that was it for Gauss's law. Now let's talk about Ampere's law. Now I've got 2 examples left, which are a current carrying wire and a solenoid. So part D, current carrying wire. Let's again have some kind of wire which now is not just charged but also carries current, which will create an electric field according to electromagnetism. And our goal is to calculate the strength of this, a magnetic field, I meant to say. And our goal is to calculate the strength of this magnetic field. So there's a current I flowing, and there will be a magnetic field which will go somewhat around. Oh, well, that wasn't too nicely drawn. Somewhat around that wire. Okay, so our goal is now not to choose an area anymore, but a closed loop which encloses an area which is penetrated by a current. And I would say we should choose our area to be, or our closed loop to be, maybe just that one, which is parallel to the magnetic field, always. But there's no case in which this symmetrical closed loop is not parallel to the magnetic field which is induced by the current. So we can write down Ampere's law, which is, again, closed loop, BdS equals 0 times current. And again, we can omit the vectors because they're parallel, so we don't need them. And we can pull the b outside of the integral, which gives us b times integral ds equals mu0 times I. Okay, so what is integral over ds? Well, it sums up all the little ds's, so all the little segments of our line. And when our line has radius r, obviously the sum of all the s's are the circumference of the circle, which amounts up to be 2 pi r. Let's just copy the b and that part. And if we pull that one to the other side, we get b equals mu0 over 2 pi times I over r, which is the magnetic field of a current carrying wire at distance r. And maybe one last example, a solenoid, which is basically a coil whose length is far more, or is larger by far than its diameter. So much bigger than the diameter. Because that makes the magnetic field in the solenoid quite homogeneous. So we have this coil, or this solenoid, which is obviously penetrated by some kind of current. And now the question is, how strong is the magnetic field in the inside? Because on the outside it's 0, obviously. So we could show that with some more physics. I'll omit that in this video. We know, or let's just use as a premise that the magnetic field on the outside should be 0. So the question is, what's on the inside? I'll just do another closed loop, which looks like that. So through the inside, out, and on the outside. And the only part of this loop which will be important later in the integral is that part, because like there, and there, the magnetic field will be 0. So the only thing which is important is that part. And again, that part is parallel to our magnetic field lines, because there's no reason why a magnetic field line should prefer going up or going down. There's no preferred direction in space. So again, the magnetic field lines are pointing that way or that way, but always parallel to our closed loop. So we can use Ampere's law now again. So closed integral, closed line integral, b ds equals mu0 times I. And we can again pull b out and omit the vectors because they're parallel, so we don't need them. So it's b times integral ds equals mu0 times I. Yep. And now I think about which amount of current penetrates the area. So the area is the green one. And let's imagine our coil has a length of L and N little windings. And per winding or per circle in the coil, there will be the current I. So the amount of total current which penetrates the area is N times I, right? So I of the area is N times the current which is flowing. And then how long is this ds thing? Well, the ds thing is just the length of the coil. So what we get is L, and that's it. So our magnetic field of the coil in the inside is mu0 times N times I divided by L. For diameter is much smaller than the length of the coil, otherwise it won't be too homogeneous and we need some more laws. But in that case, it's quite homogeneous. So we can try to maybe illustrate that with a diagram. So if we have a long coil, so a solenoid, the magnetic field will be like quite zero on the outside and then on the inside quite 100% and then going quite rapidly down again. And if we have not a too long coil, the field will be something like, okay, 0, 0, then going up and going down again. That's why we need a long coil, because in that case, we have a quite separated magnetic field. So it's quite separated from the outside, because that's this huge and immediate cut, which isn't so present with like short coils. That's why we are specifically looking at solenoids. Yeah, that was it for today. I hope I could help you a little bit with some basic examples of Ampere's law and Gauss's theorem. And if there are any questions left, leave them in the comments. If you would like to recommend any topics for upcoming videos, also leave them in the comments. If you have some feedback or criticism, also leave it in the comments. And yeah, if you have been, thanks for watching.